You see molten rock and think you know what danger looks like. Glowing rivers that crawl like honey down mountainsides, but there are flows that move faster than you can run. Flows that race downhill at 430 miles per hour. Flows that travel underwater. Flows that carry 210 million cubic meters of rock through the air in 18 hours. Flows that kill without ever touching you. Which ones can you outrun? Which ones give you 17 minutes to breathe ash until your lungs fail? Kilauea volcano on the Big Island of Hawaii erupted on December 23, 2024. By November 9, 2025, the eruption had produced 36 separate episodes of lava fountaining, covering 80% of Halemaumau crater floor with 11 million cubic yards of new lava. The dual fountains averaged over 600 cubic yards per second. Mount Etna in Sicily erupted on June 2, 2025, its largest eruption since 2014, sending a lava fountain 3.4 kilometers into the air and producing pyroclastic flows that reached 6.5 kilometers high. Right now, as of November 17, 2025, 44 volcanoes worldwide are in continuing eruption status. 20 are actively erupting today. Every type we discuss is happening somewhere on Earth at this exact moment. Pahoho flows first. The name comes from Hawaii. Smooth lava, ropey surface, temperature around 1,185 degrees Celsius when it erupts. This is the lava that moves like a living thing, advancing in tows, spreading in sheets, and or snaking forward in columns. The outside cools into a flexible skin while the inside stays molten. Pahoho can flow for miles, advancing slowly enough that you can walk away from it. But slow does not mean safe. When Pahoho enters the ocean, it creates new land. Kilauea has been building Hawaii's coastline for centuries this way. The flow from Pu'u'o'o cone erupted continuously for over 35 years, from 1983 to 2018. 35 years of unbroken lava output. The Pu'u'o'o eruption produced lava that flowed across 144 square kilometers, destroyed 215 structures, and added 2.2 square kilometers of new land to Hawaii's shoreline. When Pahoho hits water, the meeting creates laze, a combination of lava and haze. Hydrochloric acid forms as seawater boils. The steam carries microscopic glass particles. Breathe it, and the acid burns your airways. The glass shreds your lung tissue. Stand too close to an active lava delta and it can collapse without warning. The new land is unstable, built on layers of fragmented rock and steam pockets. When it fails, tons of lava plunge into the sea, triggering explosions that throw rock hundreds of meters. Pahoho killed through persistence and deception, not speed. A lava moves differently, denser, more viscous. The name comes from the sound people make walking on it, a cry of pain. Awe flows measure 2 to 20 meters thick. The surface cools into a layer of sharp, angular fragments called clinkers. The rubble insulates the molten interior, keeping it hot for days. Oily advances like a bulldozer. The front steepens under pressure from behind until it breaks and tumbles forward. The mass behind rolls over the fallen clinkers. The rough surface absorbs light, making AA flows appear darker than Pahoho even when they are the same temperature. AA never transforms back into Pahoho. Once the surface fractures into clinkers, the flow is locked into its rough form. Temperature and viscosity decide which type forms. Lower temperature or higher silica content produces AA. During a single eruption, lava can transition from Pahoho to AA as it cools and slows. The transition is one way. On steep slopes, A flows can reach speeds of 50 kilometers per hour. Not fast enough to catch someone running, but fast enough to trap anyone moving slowly or carrying belongings. The weight of AA is staggering. A single cubic meter of basalt weighs about 2,800 kilograms, an AOA flow 20 meters wide, 10 meters deep, and 1 kilometer long contains 5,600,000 cubic meters of rock. That is 15,600,000,000 kilograms of molten stone grinding forward. If you value documented volcanic history and current eruption data like this, subscribe. It is the best way to support our work. Also, comment from which city you are hearing this from. This script is researched and factual, using sources from the United States Geological Survey, Hawaiian Volcano Observatories, November 17, 2025 Daily Update on Kilauea's Summit Eruption, published at 1828 UTC, and from Scientific Reports Journals, March to the Nauernosex. 2021 publication on pyroclastic density, current duration effects on humans during the 79 AD eruption of Vesuvius, specifically their research on exposure time and survival rates at Pompeii and Herculaneum. Now back to the information. Pillow lava forms underwater. When basaltic lava erupts beneath the ocean, the exterior flash cools into a glassy crust while the interior remains molten. The pressure inside ruptures the crust, and new lava bulges out, forming another pillow. The process repeats, creating chains of connected bulbous shapes, each 1 to 3 meters across. The pillows stack and tumble, building underwater slopes. Kamaewakanaloa Seamount, formerly known as Loihi, sits 35 kilometers off the southeast coast of Hawaii, 975 meters below sea level. This is Hawaii's youngest volcano, still in the submarine shield building stage. Between December 7th, 2005 and January 18th, 2006, Kamaewakanaloa experienced a swarm of approximately 100 earthquakes. The largest measured magnitude, 4.0. The southern portion of the summit collapsed, moving 100 million cubic meters of volcanic material. A crater 1 kilometer across and 300 meters deep formed. A region between 10 and 13 square kilometers of the summit was repopulated with bus-sized pillow lava blocks. Researchers found these blocks perched precariously along the outer rim of the newly formed crater. Hydrothermal discharge following the collapse indicated temperatures exceeding 250 degrees Celsius. The sudden collapse of Pele's vents, a previously stable area on the southern side, created a massive pit. Fresh pillow lava samples dredged from Kamaewakanaloa in 1978 showed glassy crusts, indicating formation within the last few hundred years. Earthquake swarms at the seamount occurred in 1971 through 1972, 1975, 1984 through 1985, 1990 through 1991, and 1996. The 1996 swarm involved more than 4,200 earthquakes. Each swarm likely marked major submarine eruptions or magma intrusions. Pillow lava eruptions pose little direct danger to humans because they happen deep underwater. But the edifice collapse they can trigger creates different hazards. When a section of an underwater volcano fails, it displaces enormous volumes of water. The debris avalanche can travel tens of kilometers across the seafloor. If the collapse is large enough and shallow enough, it generates tsunamis. The axial seamount, the most active submarine volcano in the Northeast Pacific, sits 1,400 meters below the surface, 250 miles off the Oregon coast. Researchers have monitored it for 30 years. It has erupted 3 times during that period, in 1998, 2011, and 2015. The volcano inflates like a balloon as magma accumulates, then deflates when it erupts. Scientists predicted the 2015 eruption based on the inflation rate. The seamount is approaching the inflation level that preceded the 2015 event. An eruption is forecast for 2025. When axial erupts, pillow lava forms at a rate measurable in cubic meters per second. The lava advances in lobes, building new seafloor. Hot lava, meeting cold seawater at depth, creates unique textures. Some pillows form hollow crusts with lava drips extending downward. Others split and reveal the hot interior glowing orange through cracks. The 2017 expedition to Axial documented these hollow pillow crusts and photographed mini smokers, small hydrothermal vents on the North Rift Zone. Submarine eruptions at spreading centers produce most of Earth's new oceanic crust. The mid-ocean ridge system extends 70,000 kilometers across all ocean basins. Eruptions along this system are nearly constant. Spreading rates vary from 1 to 2 centimeters per year at the mid-Atlantic ridge to 10 to 15 centimeters per year at the East Pacific rise. Basalt flows along these ridges cool rapidly into pillow forms. The North Arch volcanic field north of Oahu covers 25,000 square kilometers. The flows extend 100 kilometers north and south of the Hawaiian Arch. The youngest lavas range from 750,000 to 900,000 years old. The field consists of sheet flows and small hills of pillow lava and hyaloclastite, volcanic glass fragments formed when magma meets water explosively. Lava tubes transport molten rock beneath a solid crust. When fluid lava flows down a slope, the top and sides cool and harden while the interior continues to flow. The hardened crust insulates the moving lava, allowing it to travel enormous distances with minimal heat loss. In Hawaii, lava tubes have carried fluid lava over 80 kilometers from their source. Kazumura Cave on the Big Island is the world's longest lava tube, 65.5 kilometers long with 101 entrances. The cave rarely lies more than 10 meters below the surface. It formed between 4 and 6 centuries ago when a vent on the east side of Kilauea caldera erupted, sending lava down the northeast flank. Hawaiian lavas erupt at approximately 1,185 degrees Celsius. Air and ground temperatures are cold compared to this. The protective crust that forms prevents the lava from cooling too quickly. Over time, this crust thickens, confining the flow to an oval or a rounded conduit. Lava tubes that remain active for long periods can enlarge as flowing lava erodes surrounding rock. Given enough time and favorable conditions, this erosion carves canyons and lava falls inside the tube. When the eruption ends, or lava diverts elsewhere, the tube drains, leaving an empty cave. The interior features tell the story of the flow. Wall linings are thin layers of lava that coated the walls and ceiling. Flow ledges mark different depths at which lava flowed. Lava cycles, the most common internal feature, hang from ceilings in splash, sharktooth, or tubular varieties. Drip stalagmites form beneath tubular lava stalactites. Some stalactites grade into tubular lava helictites. Active lava tubes pose specific dangers. The roof can be thin, only meters of rock separating the surface from molten lava, flowing at highway speeds beneath. Step on a weak section, and it collapses. Skylight openings form where the roof has already failed, allowing direct views into the flowing lava. Stand near a skylight and radiant heat can ignite clothing. Methane gas, created when lava overruns vegetation, accumulates in tubes. The gas can explode. When lava enters the ocean through tubes, it builds deltas underwater. These deltas are structurally unstable. Collapse is sudden. Tons of lava plunge into the sea, flash boiling water and generating steam explosions. The explosions throw rock fragments hundreds of meters. On July 12, 2025, lava from a perched pond on the south side of Pu'u re-entered the ocean for the first time since January 27th of that year. The flow front was 300 to 500 meters wide. An unstable lava delta constructed itself 30 to 40 meters beyond the old coastline. By July 17th, blockages in the tube system caused surface breakouts. The area experienced frequent delta collapses, accompanied by explosions. Public warnings emphasized the extreme hazard. Visitors to drained lava tubes face different risks. The tubes often have dark, rough-textured surfaces with sharp edges that absorb light, reducing the effectiveness of lights. The terrain inside is uneven. Trip and you fall onto rock that can break bones. In longer tubes like Ape Cave in Washington, which extends over 2 kilometers, scrambling over rubble piles is necessary. Some piles are the size of houses. The boulders are wedged into place but not secured. Climbing these formations without protective gear, adequate light, and situational awareness can be fatal. No cell phone service penetrates the basalt. Fall and break a leg half a mile from an entrance, and rescue is complicated. Lava tube shoulders, elevated platforms along the sides, allow walking above the tube floor, but any fall from these heights onto igneous rubble is severe. Tubes can contain low oxygen areas. Carbon dioxide, being heavier than air, settles in depressions. Walk into a CO2 pocket and you collapse without warning. Hypothermia is a risk. Many lava tubes maintain constant temperatures around 8 to 12 degrees Celsius year-round, spend hours inside in damp conditions without proper clothing, and core body temperature drops. Pyroclastic flows are the most lethal lava-related phenomenon. These are ground-hugging avalanches of hot rock fragments, gas, and ash that race down volcanic slopes at speeds exceeding 100 kilometers per hour. They can reach 700 kilometers per hour on steep terrain. The term pyroclast derives from Greek. Pyre means fire. Klastos means broken in pieces. These flows consist of volcanic glass, crystals, and rocks like pumice or scoria, all heated and fragmented by explosive eruption. Temperatures inside reach 200 to 1000 degrees Celsius. The kinetic energy flattens trees and buildings. The heat ignites everything combustible. The speed makes escape impossible. On May 8, 1902, Mount Pelée on Martinique erupted. A pyroclastic flow destroyed the coastal city of Saint-Pierre in minutes. Population 29,000 in 25, 28,000 died. 2 survived in the city itself, one a prisoner in a jail cell with thick walls and a single small window facing away from the volcano. The other survivor was a shoemaker on the city's edge who ran into a boat and rode the flow-induced surge out to sea. This remains the deadliest pyroclastic flow event in the last 2 centuries. The flow that hit Saint-Pierre traveled at estimated speeds over 160 kilometers per hour. It carried boulders, ash, and superheated gas. Buildings exploded from thermal shock. Stone walls a meter thick shattered. Metal twisted. The harbor boiled. Ships capsized. Bodies found later showed no signs of struggle. Death was instant. On August 24th to 79 AD, Mount Vesuvius erupted. Pompeii and Herculaneum, 2 Roman towns on the volcano's flanks, were buried. At Herculaneum, closer to the vent, pyroclastic flows reached temperatures exceeding 820 degrees Fahrenheit, possibly as high as 500 degrees Celsius. The flows killed instantly. At Pompeii, farther from the source, flows arrived with lower temperatures and reduced force. Recent research published in Scientific Reports in March 2021 analyzed the duration of the Pompeii flows. The mechanical and thermal effects were low enough that survival should have been possible if the flow lasted only a few minutes. But calculations demonstrated a flow duration of 17 minutes. 17 minutes of breathing suspended ash and superheated gas. The ash blocked airways. Lungs filled, victims suffocated while trapped in oven-like conditions. Corpses showed no signs of traumatic injury, confirming asphyxiation as the cause. At Herculaneum, hundreds of residents fled to the beach and took shelter in stone boathouses called fornici. 12 boathouses, 340 skeletons recovered. Earlier analysis suggested the victims' blood boiled and their skulls burst from internal pressure. More recent bone analysis disputes this. Temperatures in the fornici were likely no higher than 440 degrees Celsius, hot enough to kill, but not hot enough to vaporize tissue or boil blood. The victims died from asphyxiation. The fornici had only one entrance. Once debris covered that entrance, the structures became ovens. No air entered. Dust, heat, and toxic gas filled the space. Darkness. People died slowly over minutes, not instantly. Pyroclastic flows form through several mechanisms. Most result from the collapse of an eruption column. During a highly explosive eruption, material is blasted upward. If the column becomes too cool and dense to maintain upward momentum, it collapses. Gravity takes over. The mixture of hot gas, ash, and rock fragments flows downward like an avalanche. Another formation mechanism is lava dome collapse. Lava domes are steep-sided piles of viscous lava that accumulate near a vent. These domes can be hundreds of meters tall. When a section of a dome collapses, it fragments. The hot material mixes with air and volcanic gases, generating a pyroclastic flow. Block and ash flows are a specific type associated with dome collapse. These flows consist of a basal avalanche of large angular blocks that hugs the ground, overlain by an expanding turbulent ash cloud. The ash cloud rises above the basal flow due to convection. The blocks in the basal layer can be the size of cars. They roll and bounce downslope, crushing everything. November 13th, 1985. Nevado del Ruiz volcano in Colombia erupted at 9:09 p.m. The eruption was not large. The volcanic explosivity index was 3R, moderate. But Nevado del Ruiz is capped by glaciers. The explosion melted an estimated 10% of the ice. 43 million tons of water released. This water mixed with ash, rock, and volcanic debris, forming lahars, volcanic mudflows. 3 separate lahars descended the mountain. The largest traveled down the Lagunillas River Valley. Speed estimates for the flows range from 30 to 60 kilometers per hour. The town of Armero sat 48 kilometers from the volcano in the valley below, built on an alluvial fan that had hosted lahars in 1595 and 1845. In 1595, 3 Plinian eruptions produced lahars that killed 636 people. In 1845, earthquake-generated mudflows killed 1,000 people. By 1985, memory had faded. Armero was the 3rd largest town in Tolima Department, population approximately 29,000. A major agricultural center producing 1/5 of Colombia's rice. The lahars reached Armero at 11:35 p.m., 2 hours and 26 minutes after the eruption. The first wave was cold mud. Witnesses described a frightening noise, a blast of wind, then fire falling from the sky. The flows buried the town under mud 2 to 5 meters deep. Width of the flows varied from 300 to 400 meters in narrow sections to 2.0 to 2.5 kilometers in fan areas. Over 21,000 people in Armero died. In Chinchina, on the volcano's western flank, lahars buried low-lying neighborhoods. 1,000 died there. Total death toll, 23,000 to 25,000. This was the 4th deadliest volcanic disaster in recorded history. After Tambora in 1815 with 92,000 were. Krakatau in 1883 with 36,000 died, and Mount Pelée in 1902 with 30,000. Geologists and officials had warned for months. Seismic activity increased in November 1984. By September 1985, hazard maps existed. Evacuations were recommended. The warnings were not fully heeded. On the night of November the 13th, a severe storm restricted communications. Thunder and rain overpowered the volcano's sounds. At 9:45 p.m., civil defense officials from Ibag and Murillo tried to warn Armero. They could not make contact. The mayor of Armero was heard on a ham radio saying he did not think there was much danger, moments before the lahar overtook him. Lahars are a mixture of water, rock, and volcanic debris that behaves like wet concrete. Density can reach 2.5 grams per cubic centimeter, twice the density of water. The flows are not purely fluid. They carry boulders weighing tons. These boulders act as battering rams. Structures hit by lahars do not merely flood, they are smashed and buried. The mud is cohesive. It sticks. Once it stops moving, it hardens. Victims trapped in lahars cannot pull themselves free. Rescuers cannot dig them out quickly. Omaira Sanchez, a 13-year-old girl, was trapped in the Armero lahar. Debris pinned her legs. Water and mud surrounded her. Rescuers reached her. They could not free her without amputation equipment, which was not available. She remained trapped for 60 hours. Cameras recorded her ordeal. She died on November 16th from exposure and gangrene. Her photograph became iconic, representing the preventable nature of the Armero tragedy. If you value documented volcanic disaster analysis and geologic hazard research like this, subscribe. It is the best way to support our work. Also, comment from which city you are hearing this from. This script is researched and factual, using sources from the United States Geological Survey report on Nevado del Ruiz, published in the Scientific Event Alert Network Bulletin Volume 10, Issue 10 in October 1985. Smithsonian Institution, DOI 10.5479/sci.gvp.cion 198-510-3510200, and from the National Research Council's 1991 detailed study titled The Eruption of Nevado del Ruiz Volcano Colombia. South America, November 13, 1985, DOI 10.17226/1784. Now back to the information. Lava domes are among the most unpredictable volcanic features. Unlike fluid basaltic flows, dome-forming lava is viscous. Typically andesitic or dacitic in composition, it does not flow far from the vent. Instead, it piles up, creating steep-sided mounds that can grow hundreds of meters tall over weeks or months. The growth process is episodic. Lava extrudes, cools, hardens, more lava pushes up from below. The dome inflates, pressure builds. At some point, a section fails. Mount St. Helens in Washington state experienced catastrophic dome collapse on May 18, 1980. The volcano had been bulging for weeks. A magnitude 5.1 earthquake at 8:32 a.m. triggered a massive landslide on the north flank. The landslide removed the upper 400 meters of the volcano in seconds. This unloaded the pressurized magma chamber beneath. A lateral blast erupted at over 500 kilometers per hour, devastating an area of 600 square kilometers. The blast was not a typical pyroclastic flow. It was a sideways explosion of superheated gas, steam, and pulverized rock. Everything within a 17-kilometer radius was obliterated. Trees beyond that, up to 30 kilometers away, were flattened but not incinerated. The directed blast killed 57 people, including volcanologist David Johnston, who was monitoring the volcano from an observation post 9 kilometers away. His last radio transmission, Vancouver, Vancouver, this is it. Then silence. The landslide debris traveled 28 kilometers down the North Fork Tuttle River Valley at speeds up to 250 kilometers per hour. The debris averaged 45 meters deep. Maximum depth, 195 meters. Volume, 2.3 cubic kilometers. This is the largest landslide in recorded history. The debris dam formed Coldwater Lake, a separate mud flow with a mortar-like consistency mobilized in the early afternoon. By 2:30 p.m., the flow destroyed Camp Baker. 7 bridges were carried away. 3.9 million cubic yards of material entered the Columbia River, reducing the river depth by 25 feet over a 4-mile stretch. Ocean-going freighters could not pass. Portland lost an estimated $5 million while the channel was blocked. After the May 18th collapse, a new lava dome began growing inside the crater. Between 1980 and 1986, 17 smaller explosive eruptions built the dome in stages. Each dome-building episode involved slow extrusion of viscous lava. The dome reached 1,000 meter wide and 300 meters tall. From 2004 to 2008, renewed dome growth added more material. The dome swelled at a rate described as a truckload per day, nearly 300 meters of new rock in 2 months. Geologists worried constantly about collapse. Molten rock glowed at 775 degrees Celsius, only 10 meters beneath the jagged surface. If the dome became too tall or unstable, it could tumble. Exposed molten rock would explode as pressurized gas released. The primary concern was an ash cloud rising tens of thousands of feet, threatening aircraft. Another risk was that lava would melt the crater glacier, which had reformed inside the crater, triggering lahars. Soufriere Hills volcano on Montserrat in the Caribbean has been erupting since 1995. The eruption is characterized by cycles of dome growth and collapse. By 2025, the volcano has transitioned to a prolonged pause, with the last significant dome growth ending February 11th, 2010. During the active phase, the lava dome grew to over 240 meters tall. On June 25th, 1997, a large section of the dome collapsed. Pyroclastic flows swept the north flank toward the sea. A column of ash shot 9,000 meters high in minutes. Thick mud rain fell amid lightning. Darkness covered the island. The flows and mud rain lasted 25 minutes. 150 homes destroyed. 8 dead. 11 missing. In the days that followed, smaller dome collapses sent pyroclastic flows down both northern and western flanks. Flows invaded the capital, Plymouth, population 5,000, which had been evacuated months earlier. The entire city choked in ash. Buildings along the riverbanks were destroyed. On December 26th, in 1997, a Boxing Day collapse was even larger. Major sector collapse followed by explosive dome disintegration occurred at 3:01 a.m. local time. The debris avalanche and pyroclastic flows were the largest of the eruption to that point. On July 12th and 13th, 2003, Soufriere Hills produced the largest lava dome collapse in recorded history. 210 million cubic meters of dome material collapsed over 18 hours. Volume flux during the most intense phase approached 16 million cubic meters over 2 minutes. Pyroclastic flows reached the sea. The flows built a delta covering approximately 1 square kilometer. Water boiled as flows passed over it. The exact trigger for dome collapses varies. Some result from gravitational instability as the dome grows too steep. Others are triggered by rainfall. Heavy rain on a dome can cause mechanical erosion, destabilize a critically poised face, pressurize steam or water within potential failure planes, or induce rapid cooling and thermal cracking. On March 20th, 2000, a significant unpredicted collapse occurred at Soufriere Hills following prolonged heavy rainfall. Anecdotal evidence exists for other rainfall-induced activity on Montserrat and at dome-forming volcanoes elsewhere, including Marapai in Indonesia, Unzen in Japan, Santiaguito in Guatemala, and Mount St. Helens. Monitoring lava domes requires intensive geophysical surveillance. Seismic networks track earthquakes and tremor. Tilt meters measure ground deformation. Gas sensors detect changes in emission rates. Thermal cameras identify hotspots. Even with this monitoring, prediction remains difficult. Not all dome collapses display the same precursory patterns. The predictability of specific collapse events is variable. Block and ash flows are a specific subtype of pyroclastic flow associated with dome collapse. The name describes the composition: large angular blocks of solidified lava mixed with finer ash. These flows have 2 parts. A dense basal avalanche hugs the ground, carrying blocks that range from fist-sized to car-sized. Above this, a turbulent ash cloud rises through convection. The basal avalanche is where the destructive power concentrates. The blocks impact with tremendous force. Concrete reinforcement rods bend in the direction of flow. Walls shatter. Anything organic is incinerated. The ash cloud, while less dense, still carries heat and toxic gases. Breathing it is lethal. The ash is fine, often only a few micrometers in diameter. It penetrates lungs deeply. The heat sears tissue. Death comes from thermal injury, asphyxiation, or both. Block and ash flows travel at speeds between 50 and 200 kilometers per hour. On steep slopes, they can exceed this. Their density gives them momentum. They can travel up the sides of valleys and over ridges, though most follow valley floors. Runout distances typically range from 1 to 20 kilometers. In extreme cases, they can reach over 100 kilometers, though no flows of that scale have occurred in recent history. Most block and ash flows are 1 to 10 cubic kilometers in volume. The largest modern dome collapse at Soufriere Hills in July 2003 involved 210 million cubic meters, which is 0.21 cubic kilometers. For comparison, the May 18th, 1980, Mount St. Helens landslide was 2.3 cubic kilometers, 10 times larger. The deposits from block and ash flows vary in thickness. Some areas receive less than 1 meter of material. Other areas are buried under 200 meters. The deposits consist of poorly sorted rock fragments ranging from fine ash to large blocks. The matrix is often still hot when it stops moving. Internal temperatures can remain above 400 degrees Celsius for days or weeks. Anyone caught in a block and ash flow has no chance of survival. The leading edge moves too fast to outrun. The density is too great to push through. The heat incinerates flesh in seconds. The ash fills airways. Even those on the margins of flows die from burns and inhalation of hot ash and gases. Lava fountains and splatter cones represent another category of hazard. During Hawaiian-style eruptions, gas-rich lava is propelled into the air in jets or curtains. The lava reaches heights from tens of meters to over 3,000 meters. Mount Etna in Italy holds the record for the highest documented lava fountain, 3,400 meters on November 23, 2013, sustained at 2,500 meters for 18 minutes. When lava fountains, it breaks into fragments. If the fragments cool in the air before landing, they pile up as cinder or scoria, building cinder cones. If the air is thick with clasts and heat, the fragments land still molten, sticking together on impact. This forms spatter. Spatter cones are smaller and steeper sided than cinder cones. The molten droplets weld together, creating a cohesive structure. Lava fountains can feed flows. If eruption rates are high enough and fragments land hot enough, they coalesce into streams of lava. These splatter-fed flows can travel kilometers. The danger from lava fountains is primarily from fallout. Fragments rain down around the vent. Anyone within the fallout zone is struck by molten or semi-molten rock. Burns are severe. Being hit by a larger fragment is fatal. Pele's hair and Pele's tears are specific fountain products. Pele's hair is strands of volcanic glass, stretched by wind from molten droplets. The strands are thin, golden, and brittle. Wind can carry them 15 kilometers or more from the vent. Pele's tears are teardrop-shaped glass beads. Both can cause skin and eye irritation. Inhaling glass fibers is dangerous. The fibers irritate airways and can lodge in lung tissue. The November 2025 update from the Hawaiian Volcano Observatory noted that Pele's hair and volcanic fragments from lava fountains at Kilauea can be carried over 10 miles from the vent. High levels of volcanic gas, primarily water vapor, carbon dioxide, and sulfur dioxide, are a major hazard during fountain eruptions. Sulfur dioxide reacts in the atmosphere to form VOG, volcanic smog. VOG causes respiratory problems, aggravates asthma, and irritates eyes and throat. At high concentrations, sulfur dioxide is directly toxic. Breathing it causes coughing, choking, OR, and lung damage. During active fountaining, gas emissions can reach thousands of tons per day. Wind direction determines where the gas and VOG travel. Communities downwind experience poor air quality. Vulnerable populations, children, elderly, people with respiratory conditions, suffer most. Long-term exposure to VOG has been linked to increased rates of respiratory illness and cardiovascular problems in Hawaiian communities. Lava fountain activity at Kilauea during the current eruption, which began December 23rd to 2024, has been episodic. 2 vents, north and south, alternate activity. During episode 36, which ended November 9th, 2025, dual fountains produced an average eruption rate of over 600 cubic yards per second. The lava covered 80% of Halemaumau crater floor. Each episode lasts hours to days, followed by pauses of days to weeks. Between episodes, the volcano inflates as magma accumulates. Models predict the next episode, episode 37, will occur between November 21st and November 25th, 2025. This episodic pattern has not been seen at Kilauea since the 1983 to 1986 eruptions at the beginning of the Pu'u-o'o activity. Rootless cones and hydrothermal explosions add another dimension. When lava flows over wet ground, water, or ice, the interaction creates steam explosions. If lava is thick enough and the water source sustained, steam cannot escape immediately. Pressure builds beneath the lava. Eventually, the lava ruptures, steam and magmatic gases blast upward, throwing lava fragments into the air. These fragments pile around the vent, forming small cones called rootless cones, pseudocraters, or hornitos. Rootless cones are typically a few meters to a few tens of meters tall. They do not connect to a deep magma source, hence rootless. They form on the surface of lava flows. Iceland has extensive fields of rootless cones, formed when lava from fissure eruptions flowed over wetlands. The explosions that build rootless cones are violent but localized. The danger is being near the explosion when it happens. The steam blast can throw a person. The ejected lava fragments are hot. Burns are common. More dangerous are phreatic explosions, steam-driven eruptions that occur when water contacts magma or very hot rock deep underground. The water flashes to steam, expanding in volume by a factor of over 1,000. The sudden expansion fractures rock and blasts material to the surface. Phreatic explosions can occur without warning. No precursory magma movement is necessary. The trigger is simply water reaching hot rock. Phreatic explosions create craters and eject blocks. Block size ranges from pebbles to boulders weighing tons. Ejected blocks can travel over a kilometer. Being struck is fatal. The blast wave itself can cause injury. A phreatic explosion at Mount Ontake in Japan on September 27th. 2014, killed 63 hikers. The explosion occurred without warning. The volcano had shown minor seismic activity, but no alert was issued. Hikers were on the summit when the explosion began at 11:52 a.m. Volcanic ash, steam, and blocks erupted. The ashfall was heavy. Hikers near the vent were killed by blocks or buried by ash. Others died from inhaling ash and gas. The eruption lasted only minutes, but the toll was severe. Ontake is Japan's second highest volcano and a popular hiking destination. Hundreds were on the mountain when it exploded. A final category: lava flows interacting with ice. When lava contacts glaciers, ice or snow, the melting is rapid. The water generated can trigger several hazards. If the water is released suddenly, it can cause glacial outburst floods. Also called jökullaups, an Icelandic term. These floods can be catastrophic. The 1996 Gjálp eruption in Iceland occurred beneath the Vatnajökull ice cap. The subglacial eruption melted ice, creating a meltwater lake beneath the glacier. When the lake grew large enough, it burst through the ice. The flood that emerged on November 5th, 1996, peaked at 45,000 cubic meters per second. The flood destroyed bridges and roads. Debris, icebergs, harsels, and boulders were carried downstream. The volume of water released was approximately 3 cubic kilometers. Subglacial eruptions are difficult to monitor. The ice obscures the volcano. The first sign of activity may be steam rising through cracks in the glacier or seismic tremor. By the time an outburst occurs, the lake is already large. Evacuation windows are short. Iceland's system for monitoring glaciers and subglacial volcanoes has improved dramatically since the Gjálp event. Seismometers, GPS stations, and ice-penetrating radar allow detection of subglacial melt. When anomalies appear, warnings are issued. Roads near flood-prone rivers are closed preemptively. During the Bardarbunga Fissure eruption in 2014, which also occurred beneath Vatnajökull, the early detection system prevented casualties. Though the eruption lasted 6 months and produced 1.6 cubic kilometers of lava. The interaction of lava and ice creates other phenomena. Lava can tunnel beneath glaciers, melting ice from below. The water drains through basal pathways. If drainage is blocked, pressure builds. The lava can be buoyant enough to lift sections of the glacier. When the ice fails, the lava erupts through the glacier surface in a sudden breakout. Iceland's Eyjafjallajökull eruption in April 2010 began as a fissure on the flank outside the glacier, then shifted to the ice-covered summit. The ice contact created explosive phreatomagmatic activity. Meltwater flooded down valleys. Evacuations were ordered. The eruption also produced a large ash plume that disrupted European air travel for days, though this was primarily due to the explosive nature of the eruption, not the lava flows. Nevado del Ruiz in Colombia and several volcanoes in Alaska and Washington state combine glaciers with active volcanism. Any eruption that melts significant glacier mass can trigger lahars. Lahars from glacier-clad volcanoes can travel over 100 kilometers. They follow river valleys. Communities built along these valleys are at risk. The critical factor in all lava flow hazards is location. Lava flows, regardless of type, follow topography. They flow downhill, channelized by valleys and gullies. Knowing the terrain around a volcano allows prediction of likely flow paths. Hazard maps are created based on this. Areas that have been inundated in the past are likely to be inundated again. Communities built on old lava flows or alluvial fans are in the path. The Armero tragedy in 1985 was foreseeable because Armero was built on the site of previous lahar deposits. The 1595 and 1845 events should have been remembered. Hazard maps created before the 1985 eruption showed Armero in the high-risk zone. The maps were prepared but poorly distributed. On the day of the eruption, evacuation attempts were made. A severe storm restricted communication. Many residents stayed in their homes, believing the eruption had ended. The noise from the storm drowned out the sounds of the approaching lahar. By the time people realized the danger, the flows were upon them. Response time is crucial. Lava flows move at speeds that vary by orders of magnitude. Pehoho advances at walking speed. You have hours to evacuate. AA on a steep slope moves at 50 kilometers per hour. You have minutes. Pyroclastic flows move at 100 to 700 kilometers per hour. You have seconds, if any warning at all. Lahars move at 30 to 60 kilometers per hour. In the case of Armero, the town had approximately 2.5 hours from eruption to impact. That should have been enough, but communication failed. Authority figures downplayed the danger. People hesitated. By the time the mayor of Armero understood the threat, the lahar was in the town. Modern monitoring has improved. Seismometers detect volcanic tremor and earthquakes. Tilt meters measure deformation. Gas sensors track emissions. Thermal cameras identify heat anomalies. Satellite radar measures ground movement. When these instruments show changes, alerts are issued. Evacuation orders follow. The difference between Nevado del Ruiz in 1985 and Nevado del Huila in 2007 illustrates this. Nevado del Huila reactivated in 2007. The Volcano Disaster Assistance Program, created after the Ruiz disaster, assisted Colombia in improving monitoring. In 2008, when Huila erupted at 9:45 p.m., over 4,000 people were evacuated from the town of Belalcázar. A lahar swept through the town less than an hour later. No one died. The system worked. Yet prediction remains imperfect. Not all volcanic activity provides sufficient warning. Phreatic explosions, like Ontak in 2014, can occur with minimal precursors. Lava dome collapses sometimes happen without the expected seismic signals. The March 2000 collapse at Soufriere Hills in Montserrat lacked the short-term precursory activity that characterized earlier collapses. It was unpredicted. Sustained heavy rainfall was later identified as the likely trigger. Rainfall-induced collapses are difficult to forecast because they depend on weather, not just volcanic processes. The interplay of weather and volcanism adds complexity. Rain can trigger lahars even without an eruption if loose volcanic material on a slope becomes saturated and fails. Rain can also cause dome collapse through mechanisms that are not fully understood. Conversely, rain can cool lava flows, accelerating crust formation and potentially slowing advance. Wind determines where ash and gas travel. Humidity affects how ash clumps and falls. These variables make every eruption unique. Geologists study past events to understand future risks. Each eruption provides data, deposits are mapped, samples are collected, eyewitness accounts are recorded, seismic data is analyzed. Slowly, patterns emerge. But volcanoes are complex systems. Magma composition, gas content, conduit geometry, eruption rate, topography, weather, all interact. Small changes in any parameter can produce large differences in outcome. Every category of lava flow hazard discussed here is currently active somewhere. Kilauea is erupting. Etna is active. Soufriere Hills remains a threat despite its pause. Nevado del Ruiz continues to show activity. The axial seamount is inflating toward eruption. As of November 17, 2025, 44 volcanoes worldwide are in continuing eruption. The next major disaster could be years away or could happen tomorrow. The critical question is not whether dangerous lava flows will occur. They will. The question is whether people will be in the path and whether they will have sufficient warning to evacuate. The Armero tragedy shows the cost of ignoring warnings. The Huila success shows the value of preparedness. Technologies exist to monitor volcanoes and issue alerts. But technology alone does not save lives. People must heed warnings. Authorities must act decisively. Evacuation routes must be planned and maintained. Emergency shelters must be stocked and staffed. Communication networks must function under stress. When these elements align, casualties are minimized. When they fail, thousands die. The science of volcanology has advanced dramatically since 1985. Monitoring networks are denser. Instruments are more sensitive. Models are more sophisticated. The Volcanic Disaster Assistance Program has assisted in over 30 international crises since its founding. The Global Volcanism Program at the Smithsonian tracks eruptions worldwide. Data is shared. Best practices are disseminated. Yet the underlying reality remains. Volcanoes erupt on their schedule, not ours. Prediction is probabilistic, not certain. Warning times are measured in hours or days for well-monitored volcanoes, but can be zero for unexpected events. Living near volcanoes confers benefits. Volcanic soils are fertile, geothermal energy is abundant, tourism generates income. In Hawaii, the agricultural industry supported by volcanic soil is worth over $500 million per year. In Iceland, geothermal power provides the majority of electricity and heating. In Japan, hot springs and volcanic landscapes attract millions of tourists. These benefits are weighed against risks. For most people, most of the time, the balance is acceptable. Eruptions are infrequent enough that daily life proceeds normally. Farms are planted, cities are built. Generations pass without incident. Then the volcano awakens. The geological record shows longer timescales. Volcanoes that have been dormant for centuries can reactivate. Vesuvius had not erupted in at least 700 years before 79 AD. Residents of Pompeii did not recognize it as a volcano. The mountain was covered in vegetation. Streams ran down its flanks. It was simply a hill. Then it exploded. The same pattern repeats. Mount Pinatubo in the Philippines had not erupted in over 400 years before 1991. When precursory activity began, local residents did not associate the mountain with volcanic risk. Only intervention by volcanologists and the military? Arrente, Gilmais. who evacuated tens of thousands in the days before the June 15th hour 1991 eruption, prevented a catastrophe similar in scale to Armero. Even so, over 800 people died, primarily from roof collapses under the weight of wet ash. Dormancy is not inactivity. It is simply the time between eruptions. On a human timescale, a volcano that last erupted 500 years ago appears extinct. On a geological timescale, it is merely resting. This mismatch between human perception and volcanic behavior creates complacency. It is why hazard maps are often ignored. It is why people return to evacuated zones. It is why settlements are built in valleys that have been inundated before. Memory is short. Evidence is buried. The old flows are covered in vegetation. The alluvial fans look like fertile farmland. Until the next eruption, and then the pattern reveals itself. The valley floods, the slopes are scoured, the deposits are emplaced. A new generation learns the lesson. Then, in time, they forget. The difference in lava flow types discussed here comes down to composition, viscosity, gas content, and setting. Basaltic lava is low viscosity. It forms pahoho and AOA flows. It creates lava tubes. It flows for kilometers. Its gas content is moderate. Eruptions are typically effusive. Andesitic and dacitic lavas are high viscosity. They form domes. They do not flow far. They are gas-rich. Eruptions are explosive. Dome collapse generates pyroclastic flows. Water interaction adds explosive energy. Glaciers create lahars. Seawater creates pillow lava and steam. The volcanic setting determines which hazards dominate. Subduction zone volcanoes, like the Cascades, Andes, and Japanese Arc, produce viscous lavas. Domes and explosive eruptions are common. Hotspot volcanoes, like Hawaii, produce fluid lavas. Effusive eruptions and lava flows are the norm. Spreading center volcanoes, like Iceland and the mid-ocean ridges, produce basaltic lavas. Fissure eruptions and extensive flow fields result. Each setting has characteristic hazards. None is safe, but the specific dangers differ. A person living near Kilauea faces lava flows and fog. A person living near Mount St. Helens faces lahars and explosive blasts. A person living near Soufriere Hills faces pyroclastic flows from dome collapse. Knowing the local volcano's behavior informs preparation. In July 2003, the summit of Soufriere Hills volcano lost 210 million cubic meters of rock in 18 hours. Photographs from before and after show the dome reduced by nearly half. A massive scar marks where the collapse began. The pyroclastic flows that resulted traveled to the sea. They covered valleys. They built deltas. The deposits are still being studied. In May 1980, Star Mount St. Helens lost its top 400 meters in seconds. The landscape was unrecognizable afterward. Before and after satellite images show the difference. The mountain is shorter. The symmetry is gone. A horseshoe crater faces north. 33 years later. In November 2013, a detailed soil core extracted from Kilauea's south flank revealed layers of charcoal and paleosols, ancient soils. Each layer marks a period when lava covered the area, burned the vegetation, and then paused long enough for soil to form before the next flow arrived. The core records hundreds of these cycles. In Iceland, a boundary marker dug from a field shows the extent of a lava flow from the 1783 Laki eruption. The flow reached this point, then stopped. The marker was placed by surveyors afterward to document the new land boundary. Similar markers exist around Kilauea, documenting the advance of historic flows. In Colombia, memorial sites mark where Armero once stood. Crosses and plaques identify where buildings were. The mudflow deposits have hardened into a rough plain. Vegetation has returned. Without the markers, it is difficult to imagine a town existed here. But dig down and the evidence is immediate. Mud, rubble, fragments of concrete and metal, layers of volcanic ash. The stratigraphy tells the story. Everything buried under meters of lahar deposits. One event, 2 hours. 23,000 dead. Every dangerous type of lava flow explained leaves you with one truth. Proximity to volcanoes is a calculated risk. The flows move, the speeds vary. The triggers differ, but the pattern holds. Eruptions happen, lava flows. People in the path must move or die. Technology provides warning. Preparation saves lives. Complacency kills.